Okay, this is the Unit 1 review in AP Stat. Again, this is kind of going over chapters 1 through 6, just looking at as many questions as we possibly can to review. Doesn't even guarantee that these are going to be in your test. They're just a way to see where you're at for the exam. So, again, if I'm moving too fast, pause these videos, write down some of the problems so you know what's happening. But you pick up a card from a deck, which we'll be going over probability of stuff in Chapter 11, and that's 2 units from now, and record its denomination, like the 7, and its suit, maybe spades. Is the variable suit categorical or quantitative, right? So is that. Name a game you might be playing for which you would consider the variable denomination to be categorical. All right, and then name a game you might be playing for which you would consider the variable denomination to be quantitative. Okay, so you're doing the 7 of spades, is what they're saying, is picked. And they want to figure out what this is. So, is the variable suit categorical or quantitative? Well, a suit is certainly going to be a category because there are 4 different types of them. All right? You got hearts, spades, you got diamonds, you got clovers, right? It's a type, so it's a category, right? When it says, name a game you might be playing for which you would consider that denomination to be category. Well, a category. In the game Go Fish, for example, all right, the denomination is not ordered, all right? Numbers are merely matched with one another. That's it. That's how Go Fish works. You're just trying to match. And if that's the case, it says name a game you might be playing for which you would consider the variable denomination to be a category, right? You may have seen Go Fish decks that have symbols or pictures in the cards instead. Those work fine. Okay, so you're just trying to match the 7. It has nothing to do with the number or counting whatsoever, but it says name a game you might be playing for which the variable denomination to be quantitative. Gin Rummy, right? The order of the cards is important. If you've ever played that during the game, runs of cards are assembled and you get points for the amount that you have. So at the end of the hand, points are total from the denomination. Face cards 10. However, even in Gin Rummy, the denomination of the cards sometimes behaves like a category when you're collecting 3s, for example. But it's an example where you add up and find the total points when it's all said and done because you're counting with it. All right, so it just depends on the game with the cards. Taking a look at this one, in an investigation of environmental causes of disease, data were collected on the annual mortality rate, deaths per 100,000 for males in 61 large towns in England and in Wales. In addition, the water hardness was recorded as the calcium concentration parts per million ppm in the drinking water. What are the variables in this study for each indicate whether it's quantitative or categorical? Okay, so what are the variables in each? So here's what I did. They give you the graph already, and this is the graph for calcium and morality. So you're looking at 2 different histograms here. Okay, so as you're looking at this, the variables in this study are both quantitative. Now, what would be your big clue with that? We're talking about histograms here. So more than likely it's going to be quantitative. We're also talking about numbers of something. Now, I know numbers can still represent a quality, as in like some kind of category, right? They can. But we're talking about adding up the hard water with these, and we can do numbers, we can do operations with them as well. So the variables in the study are both quantitative. Annual mortality rate for males is measured in deaths per 100,000. Calcium is measured in parts per million. They're measured in numbers. So that would be the case. And here are the histograms, right? It says describe the distributions. Well, this one definitely looks skewed to the right, which means I'm going to probably be using a median interquartile range, and the mean is pulled down a little bit because of that. This one is definitely more unimodal. So because it's definitely more unimodal, that means I'm probably going with more of the mean and standard deviation when looking at these. So once again, it says the distribution of the calcium is skewed to the right. All right. And it says with many towns having concentrations below 25. right? If I split this up, many of them are below there. The rest of the town have calcium, which are distributed in fairly uniform. Like the rest of it, for the most part, it's fairly uniform, tapering off when we get higher up there. But the distribution of morality rates is unimodal. It's symmetric with a center approximately at 1,500. The distribution does also have a range from 100 to roughly 1,000 to 2,000 as its range. So we could try to find the standard deviation in order to do this as well. The data set from England and Wales also notes for each town whether it was south or north of Derby. There are some summary statistics to compare with the box plot for the two regions. So north versus south, right? Summary of the morality. Of the mean of each, the median of each, the standard deviation of each, the counts. So I'm able to kind of do a box plot of each, which was given. So you can take a look at the box plot, and it looks like the morality rate in the south, everything appears to be lower. I mean, even the amount, the low, even the range of everything, your interquartile range is even lower in the south. So what is the overall mean morality rate for the two regions? All right, so what can you do with the two regions with the overall mean morality rate, and do you see evidence of a difference in morality rates? So the overall mean morality rate is, that's the mean, right? And there's 34 counts of it. That's the mean, and there's 27 counts of it, and then the number of counts. So we end up with that, deaths per 100,000, that's the mean overall. So that would be the mean overall, and then it says the distribution of morality rates from towns north is generally higher than the distribution of morality rates from the south. Fully half of the towns south of the Derby have morality rates lower than any of the towns north. A quarter of the northern towns have rates higher than the south, right? I mean, just think about it here. Mostly all of these are lower. That is 75%. Almost all of the 75% are lower than majority of their data. So the morality rate is naturally higher for the north in general than it is for the south. Avoiding an accident when driving can depend on reaction time. That time measured from the moment the driver first sees the danger until he or she steps on the brake pedal is thought to follow a normal model with a mean of 1.5, standard deviation of 0.18. It says use the 68, 95, 99.7 rule to draw the normal model. Write a few sentences describing the driver reaction times and what percent of drivers have a reaction time less than that. So we'll definitely need a calculator to start a lot of this. So the normal model, again, you just basically take your 1.5 and then you take your 0.18 and you add them up and you subtract them down. So you get your 68, 95, and 99.7. So there is your normal model. Now it says to describe driver reaction times, and it says the distribution of reaction times is definitely unimodal. It's symmetric. The mean's 1.5. The standard deviation is 1.5, but that was basically all given. And according to the normal model, 95% are the drivers are expected, and you look at this, 95% are expected to be between 1.15 seconds and 1.14 and 1.86 seconds. So you can just kind of look at that to see. It says what percent of drivers have a reaction time less than 1.25. So again, when I'm looking for a percent, I would do normal CDF, and the fast way to do this is second vars, go down to normal CDF. And because I'm looking for 1.25 seconds, but I want low to high, I'm going to go with negative like 100, comma 1.25, comma 1.5 is my mean, comma standard deviation is 0.18, and when I press enter, I get the 8.24 on the button. You could have also found the z-score by just doing something like negative 10 to 1.25, comma 0, comma 1 to get the same thing. But you would have gotten the z-score, then you have to find what it is. When we're doing this, and there's the z-score, sorry. What percent of drivers have reaction times less than 1.25? Did that one. What percent of drivers have reaction times between that? So I would just do second vars, normal CDF of 1.6 to 1.8. And then the mean is 1.5, comma, the standard deviation is 0.18. And I get roughly with this one 24.13-ish%. Technically, I'm getting, on my calculator, I get more like 24.15%. You could do it all in one-stop shopping instead of switching it to z-scores. Then it says, what is the interquartile range of the reaction times? Well, that means I need to find the low 25% and I need to find the low 75%. So now, because I'm doing percentages, I would do second vars. I would do inverse norm to find the percent, the 0.25 of. Since I know the mean and I know the standard deviation, I plug those in with commas, and I get that this first quartile is roughly 1.38. I now need 0.75, so I do second vars. I do inverse norm because I'm looking for a percent, and from here down is 75%, so 0.75, comma. The mean is 1.5, comma, and the standard deviation is 0.18, and that is roughly 1.62, so I subtract the two to get about 2.4 seconds. Would be the interquartile range. And then it says describe the reaction time of the the slowest one-third of all drivers. Well, slowest one-third of all drivers. If I want the reaction time of the slowest third of all drivers, then when I look at this, that is the percent of the 33.33%. But to figure out what that is, people end up getting confused with this, and I was as well for a second there. It says slowest reaction times. Remember, these are actually faster reaction times. People see slowest and they think you want to go down this way, but technically these are faster reaction times down here. If I'm reacting in like 0.8 seconds, that's really fast. The slowest is down here. So the way the problem is worded, you think you want the slow end that way, but it's technically up here is the slower one-third. Well, 33.3, which means the other end is 66.666. So I would go to second vars, and since I know the percent of the inverse norm is 66.666, you just start writing 0.666 a whole bunch of times. 1.5 is the mean. 0.18 is the standard deviation, and I am getting 1.5775 or 1.58 seconds when I plug it in right on the button. So, slow reaction times, right? Remember, that is a high reaction. I don't want it to be high, but I'm just saying, if you're going slower, there's more time that it takes. All right, we will take a look at these when we come back with some more examples from Unit 1 and our review.